Good. So the first thing we are asked is about the limit when x tends to -1 of this function. We don't know which function it is. I can spoil you that it's a parabola because parabolas are beautiful and have some very interesting properties. But we're looking at this function. The limit of a continuous function in a point where it's defined is the value of the function. So we check that the function has a value on x equal -1. And what we have is that this is the function evaluated in -1. And as we are seeing in the graph, this is 1. Now for the second. Limit when x goes to 0 of f of x. You will generally see a lot of people writing this in this way. But that's writing a little bit too much. In the question, it is an open circle. It's not an open circle. It's actually a parabola. It's this curve over here. Now, the point at -1. You are right. You're right. This point doesn't exist. So let's go all the way back. So the function is not defined in -1. So what we have to evaluate here is the lateral limits, the limit from the left and the limit from the right, and see if they're equal. We don't have the equation of we don't have the equation for this parabola. It's probably something like this, but I'm not entirely sure. So we're going to forget the equation. And what we have here is that both side limits, if you approach the function from the left and if you approach the function from the right, they go to the same point, and that point is -1, 1. Okay? So in this case, you could say and that's 1. Now, the second case is exactly the same. That's correct. We have to approach the function from the left. It goes to the 0, 0. We approach the function from the right. It goes to the 0, 0. So both side limits coincide. So that is the limit. And in the third case, we have limit when x tends to 1. And in this case, the function is defined in 1. So the limit in that point is exactly the function evaluated in that point. Now, answering your questions, it can happen that the function is not continuous, and this is the kind of discontinuities that we may find. Okay, a function is not defined in one point, and in that point it's completely different than the graph. This is I said earlier that this looked like a parabola y equal x squared. It's obviously not, because those points are jumps. And so what we want to express here is that sometimes the limit of the function doesn't coincide with the function itself. like this. So these are known as jump continuities or punctual jump discontinuities or punctual discontinuities. And they are probably the most common. When you're working with a function like this, the most common thing you can find is that either there is no function at this point, or the function is somewhere right here. It happens. So I'm going to notice here. And we have A, we have B, and we have C. So we can call this problem solved. Now, any further questions? Okay, then if it's all good, we are moving on to the next. Number 11. Are you allowed to speak while the tutorial is being recorded? Yes, you are. I actually encourage you to do so because the laptop is not at a very proper distance. So we can see how that works. The only thing is, please don't speak two people at the same time. But otherwise, yeah, questions are allowed. You're allowed to ask, speak. It's a good thing that you are not that many people, because that means asking verbally is something we can do. All right. So yeah. Now for number 11, we are asked to evaluate the limit when x tends to 1 of x squared minus 1 divided by x plus 1. So when we are solving this type of limits that involve elemental functions, especially polynomials, roots, trigonometrics, and that sort of function, the first thing we have to do always is try and evaluate it. If we evaluate this in 1, this is a continuous function, there is no problem with this. We evaluate this function in 1, and we see that this is 1 squared minus 1 divided by 1 plus 1, which is 0 over 2. And we're done. Now, questions about this quotient of polynomials? Good. Then I am showing you the next one, which looks a bit more interesting. We are asked to calculate the limit when t tends to 0 of t Now this looks a bit more interesting already, right? Because we have t, and here we have something that is a difference of roots, and the difference between those is when t tends to 0, this could be something like 0. So the denominator is 0. Okay, if we try to evaluate, we have 0 here, and we have square root of 4 minus square root of 4. And this is 0 divided by 0. So this is the first slight complication that we find. So what we are going to do is to try and remove this 0 from here. How we are going to do it? First, we have to assess what the problem is. The problem here that makes our denominator 0 is this minus sign here. Okay? So we have to figure out a way to get rid of this minus sign. What we are going to do is we are going to use this notable product that says a plus b times a minus b is a squared minus b squared. This notable identity, we're going to use it constantly as you have to solve limits that involve polynomials and other things that involve polynomials. This is your bread and butter. And so what we are going to do is say a is square root of 4 plus t and b is square root of 4 minus t. So this is our idea. I will have to delete. What we are going to do here, this is a, this is b, we have a minus b. We're going to multiply and divide by a plus b. So in the denominator, we have a minus b times a plus b, just this difference of squares here, and we can solve that into something that is not 0. So let's see how this works. I mean, we haven't done anything. Now I have to delete this. And this is equal to the limit when t goes to 0 and what we have here is 4 plus t minus 4 minus t. And this is the limit and 0 over minus minus plus this 4 goes away, and what we have here is 2t. But wait, this is 0 again. No worries. We're not evaluating in 0, we're calculating a limit. So another thing we can do is cancel the t that's multiplying with the t that's dividing. Is when we calculate a limit, we're not exactly on the point, but we are approaching the point instead. So we can consider that t is different than 0 always, and we can do this cancellation. So we're going to write this in a beautiful way. And now this is a function that is continuous and we can evaluate it in 0. Square root of 4 is 2. So this is 4 divided by 2. Beautiful, isn't it? I'm gonna put a parenthesis here. So this type of tricks, manipulations, and transformations is something we're going to be doing constantly when working with limits. So please keep those in mind. Now, further questions? Good to know. I did a conjugate multiplication indeed. That's way more useful than you may think, actually. Now, for our next candidate, we have exercise 75 that says the following. Okay, this is all we know about function g. It's between 2 minus x squared and 2 cosine of x squared. No, sorry, 2 cosine of x. And we are asked for the limit when x tends to 0 of g of x. So our first thing to consider here is that both these functions are defined in 0. Not exactly defined, they are continuous. Okay, this is a parabola. This is a trigonometric. Okay. This inverse A means for all. So this reads like 2 minus x squared is smaller than g of x, which is smaller than 2 times the cosine of x for all x, for all values of x. I'm going to be using this one constantly. So the first thing we notice is that these functions are continuous in x equals 0. And so one thing we can think about is that if we evaluate all this expression in 0, we have 2 minus 0 squared okay, the cosine of 0 is 1. And so 2 g of 0 is between 2 and 2. So we know it's 2. If we treat this as a limit, if g is continuous, which we know, yeah, then this is equal to the limit when x goes to 0 of g of x. And so from this double sandwich inequality, we have that g of x, the limit of g of x is equal to 2. There is one and exactly one part of mathematics that is not fun, and it's when you drop a pen on your white trainers. This may or may not have happened just now, but yeah, I'm actually very glad that you guys are enjoying it, especially this the ground courses, both vector algebra and one variable analysis. They give you a lot of basic tools that you can do very creative stuff with them, and that's the purpose of the tutorials. So, if we are all clear with this one, we are moving into section 1.3. That makes it 2 of us, MHD. That makes it 2 of us. Now let's see what else we have for today. Exercise number 3. Woohoo! This is a big limit. And up we have 3x cubed minus 5x squared. I said squared. Plus 7. And then we have x 8 plus 2x and minus 5x cubed. So this is obviously a case in which the numerator is infinite to the cube power. That kind of goes really big. And here we have the same. So what is the rule for quotient of polynomials? Limit of a quotient of polynomials in the infinite. So what we do here is we check the highest degree, okay? If the highest degree of both polynomials is the same, the limit is the quotient of its coefficients. So I can instantly say this limit is equal to minus 3 divided by 5. Give it up. Okay, so I'm going to expand a little bit of this, but quotients of polynomials have very smart. This is actually minus 3 or 5. I'm going to give you here a small table on how these limits are solved. Numerator. If the numerator is greater than the denominator, the limit is plus or minus infinity, depending on what we have here. If x tends to minus infinity, well, we put a negative sign. If the numerator is smaller and the denominator is bigger, and we are looking at this degree over here, Remember, we always look at that degree. If the numerator is smaller than the denominator, the limit is 0. And if the numerator and the denominator have the same degree, let's say this, for example, a times x to the power of n, and this is b times x to the power of n. I'm looking at these coefficients here. This would be a, this would be b. And so this limit is a divided by b. So there is a lot more reasoning here, but now that you have certain notions of continuity and limits, we can go and explain them to you. And the reason is infinity is a concept, okay? In functions, infinity talks about how fast the function goes up. So in this case, the higher the degree, the faster it goes. If you see the function of y equal x, by limit, you mean it's the value that the function approaches? Yes, I do. You look at y of x, y equal x, this is the 0.11. This is y equal x, and this is y equals x squared. And this is y equals x cubed. So the idea here is that the larger the degree, the faster the function goes. And so if one of the sides goes to infinity very fast, like faster than the other side doesn't matter. And that's why this table is so useful. Now, let's move to the next one. I wasn't expecting to find something this beautiful this soon, but the God of math has blessed us with some very nice stuff to do today. So the next exercise is number 11. One over 3 minus x. The god of math, you know, there's a lot of talk about different gods, but the god of math is by far the most merciful one, as they always provide. The god of math always provides if you have your eyes open. You don't really need faith. That's a really nice thing, but if you have your eyes open, you will always find it. Okay, so in this case, what we have is 1 over 3 minus x. This has no degree. This has degree 1. Okay? So this is important. If you evaluate this, here is where the problems begin. You may think this is infinite. This is not exactly infinite. This is not exactly infinity. Now, if we approach 3 from the left, we are using values that are smaller than 3, then this is greater than 0, right? You're 1 over 3 minus a number that is smaller than 3. This is greater than 0. And so the limit is plus infinity. So this goes up very high. However, if we approach from the right, we see the complete opposite behavior, right? We're dividing 1 by a negative amount because this is greater than 3. And so And this is the answer, okay? This is what is called a vertical asymptote. You will see it. And what this weird thing means, can't you see the whole answer? Ah, okay, it cuts right here. Okay, let me fix that. Now, much better. So we have two conclusions from this. The first one is that the limit as is written there doesn't exist. Because if you approach from one side, you get a result. If you approach from the other side, you get another result. However, what it's telling us is that we have what is called a vertical asymptote. If you were to draw this, you have here the point x equal 3. What this double limit means is that if we approach from the left, this curve goes like this. And if you approach from the right, it goes like this. And it gets closer and closer to this vertical line. This is what a vertical asymptote is. Okay, so there was actually a ton to this apparently simple thing, isn't it? All right. We will say that the function has no limit approaching 3. Yes and no. Yes, because both the lateral limits don't coincide, but there are lateral limits. So that the whole answer will be the lateral limits that I put here. The limit, that exact limit is not, it's not one and the same, but there are two different ones. Oh, this is a good one. If the question was, does a limit exist? We would have to show all the work that you showed. Yes, you should. And what you should do then is specify that if you approach from the left, you go up, and if you approach from the right, you go down. That sort of discontinuity is called vertical asymptote, and that's the correct answer. The complete answer. Now, absolute value. Okay, I accept ideas on how to solve this one. Okay, then I'm going to give you my own. And we are going to base ourselves in this realization. This is always greater than 0, right? Greater or equal than 0. you know, the problem if you evaluate this in 0 is that 1 over 0. And so. If we approach x from the right, then this is true. And so our limit becomes 1 over x minus 1. They say time to resubmit. Now, if you only said that the limit doesn't exist, then it's fine because you're actually not supposed to know about asymptotes yet. So that will not be a problem. Now, what we have here is this limit. You evaluate this. This is either plus or minus infinity. But since we are approaching 1 from the right, x minus 1 is always greater than 0. And so our function goes to plus infinity. Great. Which example is this? This example is number 21 from section 1.3. It's the last exercise from section 1.3 that we'll be covering, but now we're moving to section 1.4 that talks about continuity. Okay, so I'm going to start with number 14. Sorry, 13. And it says, okay, this function is missing a point. I said that if the degree of the denominator is larger than the degree of the numerator, the limit is 0, but only in the case where x goes to infinity. The rules for polynomial quotients that I gave you here only apply if x goes to either infinity or minus infinity. Otherwise, you have to go and evaluate and do some manipulations with the polynomials. Now, okay, this function is defined on every point but 1. So what we are going to do here is try and solve the limit when x goes to 2 of this function here. Now, once again, we're going to split the numerator because this is obviously 0, so we will have a problem. We can't define the value of a function to be infinite. And so what I'm going to do here is split the numerator as this product. Now that is defined here, and we know that we are calculating a limit and not exactly evaluating a function, then this term and this term have the common decency of canceling each other out. And so we are left with the limit when x tends to 2 of x plus 2, and that's 4. So the answer to this problem is we should add 0.24 to this function. So we have to define it, and we say f of 2 is 4. And now we're finished. Remember that many of the times the purpose of a problem of mathematics is not always related to the tools you use. So in this case, the solution is not the limit. The solution is we have to add a point. So always check your conclusions and be sure to explain them properly. Now, number 29. Okay, oh, that's right. It's 11:05. So I'm going to write problem 29 in the whiteboard, and you can take 15 minutes in the meantime, and when we're back at 11:20, we will solve it. All right? Okay, let's move. Welcome again. Now we want, let me see if I wrote the polynomial properly. Yes. Could we do question 25 after this? We absolutely can do question 25 after this. But now, we have to show that there's a point between 0 and 1 where this function is negative. Okay, so the first thing we are going to do is evaluate f in 0 and 1 and see what happens. This is 0 cubed plus 0 minus 1. That's minus 1. And this is 1 cubed plus 1 minus 1. And this is 1. So what's the key here? F of 0 is smaller than 0. F of 1 is greater than 0. Now there is a result. Let me see if I can read it literally for you. Is it not here? Yeah, here. It's called the intermediate value theorem, also known as Bolzano's theorem. And it says, that if a continuous function goes below 0 and above 0, it crosses 0 at some point. We can call it, I don't know, like this. And we're finished. We have absolutely no way to know which point that is without solving it. It's a cubic equation. It shouldn't be too hard. There's a formula for that. But the idea is that Bolzano's theorem guarantees that there is such a point. And that's what we wanted to solve. In the book, you have this as theorem 9. And now we're going to check problem 25. Okay, we have f of x. And we want to see where it's positive and where it's negative. So x squared minus 1 is a bit difficult to manipulate in that sense because x squared is always positive. And so what we are going to do is split this as x minus 1 times x plus 1 and divide it by x. And so it looks like there are like three possible scenarios in which our function could give us problems or insight on how it works. And those are x equal 1, x equal minus 1, and x equals 0. In x equals 0, the function goes to infinity. And so in x equal 1 and x equal minus 1, the function is 0. So let's draw that. We have x equal minus 1. We have x equals 0. We have x equal 1. On the previous one, we are assuming f of x is continuous. Polynomials are always continuous. We don't have the need to assume that. They are by definition. So, if x is smaller than minus 1, like here we know that's true. If x is smaller than minus 1, what do we have here? X minus 1 is smaller than 0. X plus 1 is also smaller than 0. And x is smaller than 0. So we have negative times negative, which is positive, divided by negative, which is negative. Now, if x belongs to minus 1, 0, I'm going to note this here. This way with a bit more of detail. Yeah, it's kind of in the limit, but I think you see it. Yeah. Now, if x is between minus 1 and 0, x minus 1 is obviously negative. X plus 1, we move here, it's positive. And x is negative as well. So our quotient is negative times positive, negative, divided by negative, positive. This is abbreviated notation. Now, if x is between 0 and 1, x minus 1 is smaller than 0, x plus 1 is greater than 0, and x is greater than 0. So what happened with f of x? Negative times positive, negative divided by positive, negative. So the function is negative in this region. And finally, if x is greater than 1, x minus 1 is greater than 0, x plus 1 is also greater than 0, and x is also greater than 0. So our quotient is positive times positive, positive, divided by positive, positive. So this is how we analyze signs. You remember correctly from what the problem has told. Here we have a 0. Here we have another 0. And this is what we have seen before to be a vertical asymptote. It goes positive, it goes very positive. This limit is infinite. And when we recover the function, it is very negative. So here the function approaches this line. And yeah, it's fine. This line, I don't know, you will see with enough detail. But this is x equal -1, this is x equal 1. And so the function does something like this. Maybe it's not exactly like that, but more or less that form. It starts negative at -1, it crosses the line, it comes as positive as it can. In 0, it doesn't have a function. Then it comes from below and rises. And in the extremes, in the infinite, square divided by x, greater degree, that limit is infinite. And in the other side, since we're going to minus infinity, the limit is minus infinity. So it goes down indefinitely as well. Now, there was a ton of use to this exercise. Now, okay, I'm going to show you now one of the exercises from part 1.5. And the idea here is to use the formal definition of limit to solve this. So I'm going to pick up a small example, number 11. And so we want to translate to mathematics the following notion. Well, this is immediate. As we know, we evaluate the function in 1, 3 times 1, 3 plus 1, 4. But we want to use the formal definition of limit, which is notation epsilon delta. Right? It says that if we pick 2 points that are closer than delta, then the difference of the images is also closer than epsilon for every epsilon. So the way we're going to phrase it here is that for all epsilon greater than 0, which is this distance, there is a delta, a horizontal distance, such that if you ever see this in a book, it means such that. It's not very used anymore. People generally prefer to write such that instead of a table, but the table is funny. It's a table. I mean, so for every epsilon, there's a delta such that if x1 minus x2 is smaller than delta, this is x1, this is x2, then we can. Now, this is how the limit is formulated in epsilon delta notation. So for every vertical distance, we have a horizontal distance such that if we have 2 points that are closer than that horizontal distance, then their images are closer than that vertical distance. This one took me 3 months back in the day. Then of course you can do some more manipulations here and say that +1 they cancel. And here we can divide by 3. And what we have here is that so if we have 2 points that are closer than delta, actually those points are closer than epsilon divided by 3 for all epsilon. Which means that the curve is very steep. Actually, it has slope equal 3. And this is delta. It doesn't look like a delta at all. And you may be wondering why this is useful. Well, one of the main characteristics of mathematical analysis is that many of the results revolve around things existing. You don't necessarily have to find a way to calculate them, but most of the times knowing that it exists is enough. And that's why epsilon delta notation is so useful. So this is fantastically good to have here. Because then by the end of the course, when you and Ashraf get with the powerful machinery and you start using cannons to kill flies, you will see this put to good use. Okay. Now, do you have any questions regarding any of these topics that we have touched, or any exercise that you feel curious about that I could show you? Something similar to question 3 of homework. Let's see. Okay. Okay, yeah, we can do something similar to this. I'm going to show you how this type of exercises works. The idea behind it is the same. You have to use the concept of limit. You know, a function is continuous. A function is continuous in x equal x0. It's equivalent to say the limit when x tends to x0 of f of x is equal to f of x0. So the strategy here is calculate the limit and compare it with the value of the function. So I'm going to show you a small example. We have fx and we wonder if this function is continuous. So what do we have to check here? Let's check it out, right? Now, on the one hand, f of 0 is 2, which is defined here. On the other hand, the limit when x tends to 0 of f of x is the limit when x tends to 0 of cosine of x. And this is 1. So if we compare these two, we see that these things are not equal. And so f of x is not continuous. And that will be it. So the big problem you may find with such an exercise is that this function here is written in a form in which it is complicated to manipulate, in which case you have to take it out into something you can work with. Okay, now to finish this class, I'm going to show you 511. So the idea behind mathematical analysis is to have very few concepts and a few tools to manipulate them and put them to the extreme. And this is what we are going to do right now. So f is continuous in this interval, and f of 0 equals f1. Okay? We want to see now, on a first glance, this is a titan, a colossus, an absolute massacre of a problem, honestly. This is scary. If you find this is in an exam, you may think, oh God, I only have 3 hours to solve this, but we have all the tools we need to solve it right now. So we're going to make it really simple. Which tools we have here? We have continuity. We have a thing called Bolzano theorem. And this is all we need. So let's see. First of all, I'm gonna do the following call. Okay. If now we traduce f in terms of g, then f of 0 this is very important, and g of 1/2 is f of 1 minus f of 1/2. Now, immediate observation. F of 0 and f of 1 are the same. We know it from the conditions of the problem. And this means that these two things are opposite from one another. G sub 0 is f of 1/2 minus f of 0, and g sub 1/2 is f of 0 minus f of 1/2. So if g sub 0 is positive, g sub 1 is negative. What does this mean? Now, I'm gonna write it here. 1 is positive, 1 is negative. Now, if we have a continuous function that is positive and then negative, which theorem guarantees that there is a point in which the function is 0? You're right. Our good friend Bolzano. And he says there is a point, exists A, in the interval we are working with, such that g of A is equal to 0. But what does g of A is equal to 0 mean? It means this is equal to 0. And then you get up in slow motion, hand in your exam, and go home. Please do all the rest of the exercises before. Otherwise, there may be consequences. But this is beautiful. So, what are the keys for these exercises? Key 1. Since we wanted to know that these things were equal, we are putting the difference. Two things that are equal, if you calculate the difference, it's 0, obviously. Then we calculate the interval we're working with. We know that A is smaller or equal than 1/2. And so our interval we have to work with is now from 0 to 1/2. We calculate them. And with this new function, we now apply the properties of the old function. And we arrive here. From here, we have Bolzano's intermediate value theorem. And what do we have? This function is 0, but what this function is the difference that we were looking for. This is my favorite type of problem by a mile. Now, now let's play a game. Let's play a little game. So I'm going to propose you a small problem, a small limit. And the first one to write the answer in the chat will present tomorrow. In the next Monday, there is the first assignment in which you have to present problems. All of you are going to eventually present one, but you may want to present first, as you know, less pressure, less tension. So let's do it. The first person to solve this problem in the chat can choose. All right. We have a winner. Congratulations, Steven. -1/3. You compare the degrees, they are equal. So the quotient is the reason between the exponents. Now let me note this down somewhere. So among all exercises in the assignment, you choose which one you will present to us. Okay. So don't worry, reflexes are a skill. They can be trained. And so the last three of you who have answered, namely Marco, Steven, and Gavilla, will present your exercises in Monday for the first assignment. Now let me see how many of those I have to correct. Yeah, it's all you three. Monday. Yeah, you present them on Monday. The deadline to hand them in is 10 p.m. tomorrow, but presentation will take time in tutorial 3, which is Monday, 10 to 12. Now, the way this subject works is you will have a presentation every week. Every Monday, 3 of you will present the exercises from that week's corresponding assignment. Will we play this game again next week, Thursday? Maybe. Yeah. If I figure out a list of problems that are this fast, we may play it again. Now, on Monday, Steven, Gavilla, and Marco will be presenting their exercises. Also, for the rest of you, please don't sleep, because you may be asked about something as well. Regardless, get them ready. If you're using your phone for Zoom, there is a very quirky way to do presentations that works. That is actually holding your phone as your hand was a tripod. It's not suited for a large amount of times, but since you have this, you have pretty short exercises to show. You can use your phone with one hand and the pen with another. I've done that already. It's not too practical, but for a small amount of time, it will work if there's an alternative. Otherwise, I think we're going to call this a day. I am very happy that all of you have showed up today. I will upload this to Canvas, MDH Play, YouTube, and other sources as soon as I can. So you have access to it. And with that, if I remember correctly, we have a workshop tomorrow. I think it's from 1 to 4. We check here with the study guide. Wait, where's the schedule? Where's the schedule for this? Canvas is a little unnecessarily confusing sometimes. Okay, I may be wrong. It doesn't appear in my schedule, but I will inform you. I'll inform you about it as soon as I can. Basically, the idea of Friday workshops is something similar to this, but instead of me doing the exercise and then discussing them, it's you who do them. And after that, we will go and cover some more. Tomorrow, no one presents. Presentations are on Monday. The first 20 or 30 minutes of the tutorial will be presentations of assignment number 1. Tomorrow is your deadline to finish the assignment so I can grade them. Exactly, 1 to 4. So I will be either here or in another room, but the structure this time is I will give you a list of proposed problems and you will work on them. And whenever questions arise, I will pick up the whiteboard and fix them for you. And with all this solved, I think, guys, we can call this a day. Thank you very much for joining. I will see you tomorrow. And yes, stay hydrated.
Thank you, sir. Good one.
Thank you very much.